As mentioned previously, just because we can write a balanced chemical reaction does not mean that we have an understanding of whether that reaction actually occurs, nor how fast it goes. So in this section, we're going to talk a little bit about how we can affect how fast a reaction occurs, what we call the reaction rate. Reaction rate is measured as the amount of reactant converted to product over a certain period of time. So that means that a fast reaction rate, a high reaction rate, will mean that it goes from reactant to product very quickly. But given in the same amount of time, a slow reaction will go very slowly. We won't have very much product produced in that same amount of time. That doesn't mean that the reaction doesn't go eventually. It just means that it might go slowly. So as chemists, we usually want to increase the reaction rate, although sometimes we want to slow it down. We're going to look at some things that increase the reaction rate. Anything that increases the number of collisions or the effectiveness of those collisions will increase the reaction rate. The four major things that we use to increase the reaction rate is the size of the particles, the concentration of the reactants, the temperature, and catalysts. By definition, a catalyst is a substance that increases the rate of a reaction without itself being consumed in the process. We'll go into each of those next. The first factor that we're going to take into consideration for increasing the rate of a reaction is the size of the reacting particles. To understand this difference, we're going to look at one large crystal versus a crystal that has been crushed, so it has lots of small particles. The reaction can only occur where collisions are happening, and so that only occurs on the surface of your crystals. In the case of a large crystal, there is a large surface area, but it is all around the crystal. The center particles cannot react. In the case of the crushed crystals, while you may be able to see that there's smaller surface area for each crystal, the total surface area is much larger. Fewer of the particles are buried to the inside, and so this reaction will occur faster because of the smaller size of the particles. One way that we can make something even smaller, down to the size of a single particle, is to dissolve it. That means, generally speaking, that chemists will generally prefer to dissolve their reactants in order to get the reaction to go faster. So that's why most reactions that you see will be in the dissolved state. And usually it's in the aqueous state because most things are soluble in water. Rarely do we want to slow down a reaction, but if you did, you would of course want to use a larger sized crystal if you were trying to slow a reaction down. A second factor that affects the number of collisions, and therefore the rate of the reaction, is the concentration of the reactants. This is particularly important for those places where you have things that are dissolved. So we're going to compare two different solutions. One is going to have one of each reactant, and the other one is going to have 10 of each reactant. And we're just going to let them mix, and we're going to see how often they collide. So the ones with one, very rarely collide because they have lots of other places they could be. The ones with 10, of course, have higher concentration, and so they're more likely to collide with each other and have a reaction. So in this case, it tells you that the higher the concentration of the reactants, the faster the reaction will occur. We can compare this to being on a freeway. If you're on a freeway and it's Sunday morning and there's only 5 other cars on the freeway and you're going 50 miles an hour, there's a good chance that you won't collide. But if you're going 50 miles an hour on Friday night and there's hundreds of cars in front of you or around you, you're much more likely to have a car accident. So the same thing happens with these reactants. The higher the concentration, the more likely they are to collide with each other and react. If you want to slow down a reaction, you would of course use a more dilute solution. Having fewer reactants around should slow down the reaction. Temperature can also affect the rate of a reaction. By increasing the temperature, you're going to increase the number of collisions. Also, you're going to increase the effectiveness of the collisions. So the temperature has two different effects. To compare this, we're going to look at a container at a colder temperature, let's say 10 degrees Celsius, with 5 particles of each reactant in it, and another container with the same concentration and the same particle size, so 5 particles of each reactant, but we're going to heat this one up to 80 degrees Celsius. As you can see, at the cold temperature, the particles are moving slowly, which means that they have a low kinetic energy. And that means that they don't have as much energy in order for the reaction to occur effectively. On the other hand, we have these ones down here where we heat them up. They're moving much more rapidly, so they have more energy. They're moving more rapidly and they collide more often because they're moving more rapidly, kind of like on the freeway. When you drive faster, you're more likely to have a collision because things are moving faster. And they have enough energy to have an effective interaction so that they will crash and react with each other. And again, we can look at the effectiveness of the collisions similar to the way that we might look at it in a car accident. If you're only going 5 miles an hour, when you bump into each other, you're probably just going to get a little ding. But if you're going 50 miles an hour, when you crash, you will do significant damage because of the higher energy of that collision. And so that gives an idea that that would have a better reaction. When they collide more, they're more likely to have an interaction. Of course, if you want to slow down the reaction, the best way to do it would be to cool it down. So by lowering the temperature, you would see that the reaction would go slower because there would be fewer effective collisions and fewer collisions overall. And the last method of increasing the rate of a reaction is to add a catalyst. Remember, a catalyst is a substance that increases the rate of a reaction without being consumed in the process. That means it's being used to help the process go faster, but at the end of the reaction, it still looks the same. You might think of a catalyst as that friend who helps you go to the club to go meet somebody new. So you want to sit at home and don't really want to do anything, but when your friend comes along and they say, hey, let's go out, they come with you, and so it's made it easier for you to go out and to meet somebody new. Now that person that's coming with you doesn't necessarily get anybody to date. They're not there for themselves. They're only there to help you go out and find somebody new. That person might be similar to a catalyst. And what a catalyst does generally is they hold things in the right position so that they're ready to react. So usually they give the right orientation. These oftentimes lower the activation energy, making it easier for things to react. And when they do react, they have more effective collisions because they're in the correct orientation. Let's look on this energy diagram to see what a catalyst would do in a reaction. So we're going to start with our reactant. We're going to go up and over so we have that high activation energy, and then the energy is going to drop down to where the product is. This is an example of an exothermic reaction. A catalyst makes a slightly different pathway because it's holding those particles in the right alignment. It makes a slightly different pathway, and you might think of that like a tunnel. And notice that the tunnel makes it a lower energy so that the chemicals can go from reactant to product more readily. Think of this like if you were riding your bike. It's much easier to go through this lower tunnel, and so more people will do that, and in this case more reactants will react because they can go through that tunnel and end up at the product side. And just like a catalyst, after the bicycle's gone through, the tunnel is not destroyed. And same thing for a catalyst. After the reaction happens, the catalyst is still there in the same place, ready for the next one to happen.